All right. Good afternoon. Hope you're doing well. Hope you survived the submission last night. So today I want to talk about join memory requirements a little bit. So just to go back to things that we talked about. There's no screen. That we talked about last week. No, not last week, Tuesday. Huh. So for those listening at home, we have no projector here. Yeah. Jæja. Ég veit ekki. Það er ekkert að gerast. Það er engin fjarstýring. Upp. Okay. Podium detect. Okay. We have something. Cool. We're live. All right, so I want to go back to Tuesday's lecture and just talk a little bit about the joint memory requirements, because this, the amount of memory that you have is really the key to how efficient your joins are. And there are differences between, I'm going to focus on short merge join and hash join that are important. And then in the short merge join, there's a talk of some optimization, and I'm going to explain this. So we'll go through this. And I want you to close your computers, pull out a piece of paper and a pencil or something, and work with me. This is working time. So do you remember the disk-based sort that we did? You remember the disk-based sort that we did? How we sorted on disk? The merge sort. Yes. We started with an initial run, filled the memory, sorted, wrote to disk, and then we were merging runs until we had the complete thing sorted, right? So let's go back a little bit and look at the memory requirements of this. Okay, but first things first. So there won't be a class on Monday, but I've already put lectures online that are recordings from last time I gave the course. And so those are in place of the lectures. There's one key lecture on optimization, then a detailed example. And so, excuse me, Tuesday. All right, so there won't be a lecture on Tuesday either. Thank you, good point. And I already put Wednesday's assignment on the web, so if you want to look at it. But this has to do with the kind of stuff we're doing now. We're going to compute the cost of running joins and so on. All right. No class on Monday. There won't be a class on Monday. Okay. So going back to the sorting. So just let's start with just sorting, not focus too much on the join. If we are given B and M, so the buffers and the size of the relation, then we should be looking at how many rounds do we need to sort. Remember, we do the initial run. That's one round. We always have to do this. And then we have to merge. And how many rounds do we need to sort? And let's start with a specific example. So we have M, which is twice the size of memory. And I want you to kind of draw, you have B buffers, and you have M, which is twice the size of memory. Now draw on your paper, the process of taking this file and producing a sorted file. Just to get in your head, how does this work? We'll go through this again together, but I want you to start. The goal is this thing is the file, or the relation, it's randomly ordered. You want to make it into something that is same size but ordered. So see if you can visualize the process on your paper. So the question was, is the same as the picture in the book? And yes, it's true. I just want you to draw it because that, to be in your hands, in your head. And when I say full initial runs, I mean that you use the entire memory to create the initial run. So you load as much as you can into memory, do quick sort or something in memory, and then you write out the sorted initial run. Sometimes in computer science, you have to draw. And for those of you listening at home, then you should be doing this the same, except that, of course, you cannot close the computer. Just close everything other than this. And if you think you're done, raise your hand. Yeah. Okay, cool. We have a winner. Well, start with initial runs and then try to do the merging part also. And, it doesn't really matter how you represent it. It's, the process of thinking about it. That's key. I know this is torture. I'm having fun. All right. So one way to visualize it, let's start with the initial run, is that you start with a part of the file and you try to load that into memory, right? So that's sort of the first part. And because M is exactly 2B, then you can take half the file and you load it into memory. And then you do the sorting, and then you have to write out to disk. And so now you have something that is half the file and it's sorted. The next step. Yeah, you just take the next part into memory, do the sort, and it's done. Then what? Then you do the merge. So you basically created initial sorted runs for all the file. And so in that case, what you have left to do is to merge, and you take, basically you start by loading, the front of this, or depending on your order, you might load the back of this, and then you create, the big thing that is sorted. And so that's sort of a visualization of this process, right? Now, one thing that is important is to think about how many buffers do we need here. What's the minimum number of buffers we need for this? Excuse me. 3, you said? Yeah. So we need 1. Okay, so let's make the buffers red. So we need 1 here, we need 1 here, and then we need 1 for the output. So that's like the minimum number. So if we assume no particular optimization and so on, we don't talk about the shadowed buffers or block IO or anything, then we have the 3. Yes, question. Okay, so the buffers that combine into 1, can they still, so you're asking if this thing here can basically fit the rest? Yeah. So you can say yes and no. I mean, what you have to do is for every IO here and here, you have to do 2 IOs. See, it just fills up twice as fast. Okay, so the buffer is basically just like a page in memory, and so in this way, once you've read the entire thing from this particular page, then you read another one into this space. And when you read one page from this initial run, you read into that same space. And then once you filled up this one, you write it out, and then you have to wait until you've written it out, and then you can start filling again. So you can say that it fits, but again, we talked about these optimizations that would make it faster and so on. But did it answer your question? No? Okay, let's try again. Right. Yes, they're all the same size. Yes. Okay. Oh, I see. Okay. All right. Okay. So what you're saying, for example, if you have one record that is filling the entire table, entire page, then you're screwed. So if both records would fill the entire space so that this particular record is bigger than the page, then you have to do something else. You're right. It's a good point. So I believe, for example, in SQL Server, I think the maximum, actually no, some systems restrict the maximum size of tuples to be smaller than a page. In other cases, you can say, well, this is kind of, you could do this internally, and so you might just accept larger tuples, or if you have the optimizations where you have blocked IO, then you kind of get away from this. So let's make the assumption that this is not a problem here, but you're right. I mean, if you have very large records, then you need to worry about them overflowing the pages. Yes. Are you able to sort blobs? Yeah. So the question is, how would I sort blobs? I would basically, I don't think you would. So normally when you have a blob, you have also some other entries in the record, and that are more likely to be sorted on. So there's some kind of ID, for example, which is typically used in a join. So that would be more likely as a sorting key. because sorting a blob, as you sort of suggested yourself, it doesn't really have a meaning, right? How do you sort pictures based on their byte order? Yeah. It's like sorting bicycles based on bananas. I don't know. I mean, it really doesn't have a meaning. So and you suggested this yourself because you're like, how can we do this? But normally when you have a blob, there is some other part of the record, and that's what you would be sorting on. What does SQL Server do if you try to sort on a blob? I have absolutely no idea. How to find out? You just try. You're right. It might just tell you this cannot be done. And that would be the sensible thing to do, is to say, there is no meaningful sort order. Lots of things you do have a sort order, but for blobs, not so much. Okay, so you couldn't order by a text field? Okay, yeah. So, text fields are sort of varchar, and then there's some text. Yeah. So text is like, it's kind of like a blob, but made of text. And so that it has some characteristics. If it's big, then it's stored somewhere else, and so on. And so that might be a thing that you cannot sort on. And again, you can sort on the first part, but that's not really meaningful for text. So it's a good question. Yeah. Yes. Mm-hmm. Okay. So when we have this big buffer, you're talking about this. So then basically this actually is the zero round. So loading into memory, doing sorting in memory, and writing out, that's the zero round. It just so happens that we don't do it page at a time, we just do the full buffer at a time. And so when we're sorting this, we would probably use something like quicksort, some other memory-based sort that is efficient. So this is the round zero, and then you have another round one, and so you basically get, 2 rounds for this. So the logarithm thing evaluates to 1, and then you have the +1 for the initial round. Often I find that, doing the logarithm is confusing. You can basically pretty much do this. How many initial rounds do you have? What memory do you have to merge? And then you just do the computation until you have, you just draw until you have the final thing. So, but realizing how many buffers you need here is basically what I'm looking for in this example, because this is important. We want to see, as the file grows, how many buffers do we need? Yeah, you have a question. The M, yes. Yeah, it's a file or a table, or yeah. That's on disk. The big B, yes, that's the size of the memory. Yes, yeah, exactly. And so in this case, I set it to exactly 2. So the file size exactly 2 times the memory, just to make the computations nice. All right, so let's start another one. 4B. Now it should be quick to draw, but think about the memory requirements. How many rounds? What are the memory requirements? Yes. Right. Yeah. So the question is when I'm asking what the memory requirements are. So in the first round, we use the whole memory. When we're doing the merging, how much memory do we need to do the merging with very, very basic techniques? And so the point of asking that is because I'm going to get to how, what is your memory requirement for an arbitrary M? I want to compute that. And what's the largest file we can sort in 2 rounds, for example? I want to get to this. So you've done the picture. I mean, this is relatively simple. You read in the first thing, you sort it. So you got to sort it, run. You do the same thing with the next one, same thing with the third one, and same thing with the fourth one, right? And then you're doing the merging. And because you have lots of memory, you can do the whole thing at one time, right? Because you can basically, you have B buffers. So that means you can just read the first thing here, first thing here, the first thing here, the first thing here, and then you need one buffer for the output. So you were probably drawing 2 merges, right? Yeah, but you have B buffers. So so that's, the other one is correct if you restrict yourself to 3 buffers, but if you go this way, then how many buffers do we need? We need 5, right? So, and as long as B is less than or equal to 5, we can do this, right? If B is smaller than 5, then we're in trouble. Then we'd have to go to 2 more merges. Yes, okay. One B is all the memory you have, yes. Well, if B is smaller than 5, then you can't. Sorry, if B is greater than or equal to 5. No wonder you were confused. Happy now? Yeah. All right. Bonus point for checking this out. Yeah. So this is key, right? Exactly. As long as B is greater than this, then we're okay. Because we already set M to be 4 times B. So that's fixed. Yeah. So on an exam question, would I ask you if buffers are restricted and so on? Yes, I mean, typically what you need to compute the cost of a query is the buffer size and the file size. Those are the things normally, or the 2 table sizes for a join. And so without that, then you're kind of lost. So yes. So M equals 4B, and if I told you M equals 4B and B is greater than or equal to 5, then you should be able to tell me that you only need these 2 rounds. For example, you should be able to compute the cost of the sort and say this is 2 rounds. So to produce the sorted file, I need 4 times M for the IOs. 1 to read for the sorted, 1 to write the sorted thing, 1 to read the sorted thing, and 1 to produce the final output. So, right. So we have 1 IO here, 1 IO here, 1 to read, 1 to write. So for 4M would be the number of IOs you need here. So I'll remind me to, so I basically have all the exams going back to 2000 something early. So I'll put them online. You can look at the kind of questions I write. They haven't changed that much. So, okay, so basically when I said no other optimization, I was kind of lying. I basically tried to merge as many as you can. So that's a kind of optimization. All right, so that was 4b. Now do this one. M equals b times b minus 1. And again, try to merge as many as you can in the merging round. Try to use as many buffers as you can in the initial round and see how many rounds do you need to sort this. B rounds. I hope you need fewer rounds than B. Because you can merge many, many at a time, right? So the question is how, if you try drawing the picture, what is the size of each initial run and how many of them are there? And then how many can you merge at one time? So you have B in memory, and then the M is actually B times B minus 1. If we start with how many initial runs are you going to have that are sorted? Yeah, you're going to have B minus 1 runs, precisely. Because each of them is of size B. So that's the first round. One IO to read in, one IO to write out. Then you get to the merge. And you have B buffers. So that's the maximum you can use. The question is how many rounds of merging do you need to merge? So the question is, can you do it in just one more? What do you think? Yeah, precisely. So you have B minus 1 sorted runs. That means you need B minus 1 buffers for that. And that leaves one buffer for the output. And so you can do the entire thing, entire sorting here of this size. File of this size, you can sort in 2 rounds because you read all the sorted things and you do the merging and you write. That's the merge part. Are you with me on this? It's clear. So it's kind of B square, almost. What if we do this? M is B times B plus 1. How many rounds do you need? Or even, actually, what we should have done is to say M is B square. How many rounds do you need? So do the drawing. It helps to visualize. Cool. Very good. We don't. Yeah. Yeah, you could do that. Yes. Yeah. You right. So when you get to the merging round, you can basically, if you have more than fit in one merge, then you can divide them arbitrarily. Yes. Yes. You could do that. So how many sorted initial runs do we have? We have B. And we have B buffers. So how many things can we merge at the same time? B minus 1. So basically, at most, we could merge these things here. And then we could merge maybe, we can sort of naively read and write, or we might possibly omit this, or we might do as you suggested, which is to just split them into two to get sort of evenly sized runs. Well, might be better for I/O and things like this. Yes. Okay. But the point is, we need one more round, right? We basically crossed the boundary where 2 rounds are enough, and we had to do a third round. And that happened basically at B square. When the file size is memory size times the memory size, we went to round 3. And so this should answer this particular question for B, for any B and 2 rounds, what is the maximum M? B times B in minus 1. Quick way to do this is to say M has to be smaller than B squared, right? That's another way to do this. But it's the same thing. So as long as the file doesn't, isn't B square, we're okay. And that means if your computer has, let's say, 4 gigabytes of memory, with this method, you could basically go to 16 gigabytes times gigabytes if you did the basic thing. Now, we talked about buffering and all this stuff, and so you wouldn't sort. It's actually better to have fewer merges. It's better to have fewer merges and do sequential I/O. But if you're talking about the absolute minimum number of I/Os, this is what you get. And so, you get this logarithmic behavior. So this is, one number that I wanted to derive. It's really a key number. Understand why do we get this B square? Okay, so that was sorting. Now let's go to join. And we're going to remember what the sort merge join is. We sort one file, we sort the other file or the other table, and then we do the join in the merge phase. So if the files are equal size and we have B times B minus, so we have files that are smaller than, well, we can say B square, how many I/Os do we need? Think about this. You need to sort M, you need to sort N, and then you do the merge. And for now, let's just sort them to disk and do the merge from disk. And you should be fairly quick to do this, right? Because remember, for the sorting, we needed 4 times the file size to do this in 2 rounds. Yeah, so you have M and N, and these are 2 different files, 2 different tables, and we need to sort both of them. So to sort M, how many rounds do we need? We need 2, because we do the initial runs and we write them to disk, we do the merge and we write them to disk, and that means we have the whole thing sorted in 4M. Fair enough. And now that's on disk, and so we can clean out the buffers. We don't need any memory from this. Sorting N, how many you need for N? And then for the merge, how much do we need? And basically in the book, when they're doing the join, they don't worry about writing the output, they just ignore that. So for the merge, you just need to read one file that's sorted and read the other file that's sorted and do the merge. How many IOs to do that? M plus N, exactly. So if we add this, then we basically have 5M plus N, right? We need the 4 to do the sorting and then 1 for the final merge. And this is assuming that this B square thingy, that it fits so that we can do 2 rounds. And now you just derived, some of the formulas. What happens if we are just above, if both files are equally big and they're slightly bigger than B square? What happens here? You get an extra round, which means how many IOs? Yeah, you get 6M. N is slightly bigger, what happens? 6N, and so you go to 7, right? The merge is not affected. What if M is greater than N and one is, M is smaller than B square, N is greater than B square? So you can do the sort of M in 2 rounds, right? So you get 4M. You can do the sort of N in 3 rounds, so you get 6N. So if they're differently sized, then, then they will give you different number of rounds. Now, where would you guess, at what size of file do you think you might have to go to 4 rounds? If you just had to guess. So if you have B, you basically need 1 round, right? If you have B square, you need 2 rounds up to B square. Yeah, probably B cube. If you're less than B cube, you have 3 rounds. If you're less than B to the power of 4, you have 4 rounds, and so on. So there's a logarithmic behavior to this, and which means that the memory size is power behavior. And this is why with relatively few rounds, you can sort relatively big files. But if you look at this, which table, let's say that you have 2 tables that are different sizes, which table is more important for your memory requirements? The smaller or the bigger? Which is more important? The smaller. Can you explain why? You have to read that more often than the bigger. Really? You sure? You want to vote on this? But if you have a small file and a big file, you can see one of them has a bigger multiplication factor, right? So I think it actually, think it's the other way around, because you can see one file is growing large, and that impacts the multiplication factor. And so if let's say the case where n is very small, so I'm gonna do like this. It's much smaller than n. Who's the boss? M's the boss. You know, it's gonna go to 8, 10 IOs, and this one is gonna stay. Well, even it fits in memory. It's one IO, or 2 IOs to do the sort. But this one, logarithmically increasing. So it turns out that for the sort merge join, and we should remember this, for the sort merge join, it's actually the bigger file that's bossing the memory requirements, because we have to do the search, and we basically need to bring both into memory, and so the bigger one is the boss. So okay, so that's actually this question. If we have one file much smaller than the other, but this one is still smaller than b squared, how many i's do we need? And this we can save, maybe if m is very small, we can just read it into memory, sort it, and write it. But we still need the 2 rounds for the big file. So we're still on the order of, with, of course, the meaning of constant in order is not very practical, but we're still basically somewhere on this. We're still, maybe, this factor is only 3, but since m is the big one, no, actually, I messed the order up. Plus n, and n is the big one. So maybe this is 3, but since the larger one is more important, then we're kind of stuck with this. No, it's not really big O. Yeah, because that kills the constant anyway. Yeah. The constant is important, as it turns out. Yes. Yeah. So it's really abusing the big O notation horribly. Of course, the big O is really logarithmic, and that's where you get m log n and n log n. That's the big O thing. But since we're not in theory, we're in databases, we can abuse the logarithmic notation any way we like. All right. So let's take a break now, and then we're going to look at whether we can actually save some of these IOs by avoiding some of the writes. So 5 minutes break, and then we come back and continue. Þetta virkar. All right, let's go back. So we were looking at We were looking at the memory requirements, and now we are going to look at the case where we have files that are basically half the size of the B square. You see the divided by 2. And we're going to look at whether we can save some IOs. And so if you try to draw this process with M here and here, do the sorted runs, and then see whether you can optimize the merge part. So we're going to do the sorted runs here. And then think about how many sorted runs you have and whether you can do a little bit of optimization on the merge part. So I'll give you some time to think about this. If you do the basic thing, then you would do the merge, you would write the output, and that gives you the sorted M, and then you read the initial runs of N, and you write the sorted N. Can you start merging before? You're on the right track. Yeah. So think about this, how you could potentially do this without writing the intermediate things. Could you think of M and M as the same? Sort of, yes, but I mean, you need to worry that they're different files because that's the join. But you're on the right track that you need to somehow keep them both in memory. So let's go through this. How many runs do we have in the M file? At most. So each of them is of length B, and so at most, how many do we have? Yeah, so if, well, yeah, but what is M divided by B at most? P minus 1 divided by 2. That's the biggest value that you can have. Actually smaller than that. Okay. Of N, how many runs do you have? P minus 1 divided by 2. Same thing, at most. So how might you be able to optimize this? Yeah. Right. So the point here is that you can basically assign one buffer to each of these initial runs. And then when you do the merge, you're actually at the same time finding the smallest of this and the smallest of this, and then doing the join. And that means you only need one more buffer for the output. And what you would get from that is actually the join. It's clear. So you just saved yourself, because all you did with the sorted thing was to write it and read it. You didn't do anything else. So just by if you can fit both files into memory, the buffers for both files into memory, then you can do this in one round. Coding would be a little bit complex, right? Because you have one thing that's taking all these buffers and producing the smallest value. You have another thing that's producing the smallest value, and then you're comparing. But remember, we had the open next thing, and we just hide that beneath that. So we have a sorting operator here that's just producing the next thing, some kind of heap that's trickling the smallest thing to the top. We did this in algorithms, right, or data structures. Same thing here. And then the merge is just progressing, calling next on each side as it needs. So this is the basic trick to save some IOs. Now the book uses a slightly different formula. It basically says we'll use the replacement sort where each run is on average 2B. And that means that you can have basically half as many runs. And then they say, well, if we assume that m is and n are smaller than b or smaller than b squared, then we can do basically 3m plus n, right? Because this here, you need one IO here, you need one IO to write this, and then you need one IO for the merge. So I get 3 times n plus n. So just to point out that the book saves you the divided by 2 by making this assumption. That's the only difference between the formula they produce for this book. Right. So there is sort of a analytical way to derive the b square requirement, but this is really the best way to do it, just to make the drawing. So what we need to remember is that if the sizes are smaller than b square, then we're kind of in business. Right. So that was a short merge join. How we understand memory behavior is two things. We need to understand it's a logarithmic behavior. So if it's smaller than b, we can do it in a single pass. If it's smaller than b squared, we can do it in 2 passes. If it's smaller than b cubed, we can do it in 3 passes, and so on. And the other thing is that the memory requirement is dependent on the larger table. And that's really the key. And we'll turn out this is the key difference between short merge join and hash join, which means that short merge join is typically faster. Because we talked about this before, and we had this in the assignment yesterday. What's a typical online transaction processing workload? You have one file that is huge. This is the sales. And then you have a small customers. You have a small products. You have a small employees. Lots and lots of small files. So it's quite rare that you join two very large tables. Okay, hash join. There we have a little bit of added complexity. Remember this guy, the fudge factor. Remember what this was? Yeah. So it was 1.2. Why? Why did we need this fudge factor? Yeah. So remember hashing? Is it perfect typically? Typically slight imperfections, right? It's hard to get a completely balanced hash function that fills up all the buckets equally. And so a good hash function would normally fill the buckets like 80%, something like this. And so you get basically, if you do 1 over 80%, 1 over 83%, you get 1.2. So you need 1.2 as much memory as your file has just to fit it into a hash table. There's always some extra space. All right, so remember how the hash join went? We create a hash table. We probe with one relation. We probe with the other. So if we have one size is smaller than basically, or the file times the fudge factor is smaller than b, or we can alternatively say m is smaller than b over f. What's the IO cost? How many IOs do we need to do a simple hash join for this? And it helps, I think, to draw how you would do this. You have the m and you have the n, and we say n is a lot larger. How would you put this into memory, and what would you do? So draw. can raise your hands if you think you've done drawing. Can we store all the buckets in buffer? I would say so, because the fudge factor, because we included the fudge factor in there. Yes. Exactly. And we don't have to write the output to disk. So what you're getting to is basically you just create a hash table in memory somehow, and you put the records in there. And you don't write that. No, you just keep this in memory. What do you do next? Yeah. So we can say you apply, excuse me, n plus n, exactly. So just apply the same hash table. You go into the bucket and you check for matches, and then if you find a match, you output it. And because we don't worry about writing the output, that's basically, as you said, it's m plus n. Yeah. So do we need a buffer for the hashing? Yeah, right. So when you're hashing the values, you need a registry or something to store it. Yes. So that's very small. Yeah. But of course, this is pretty approximate. So, but we get m plus n. Can we ever do better than this to do a join? Well, if the join doesn't have any other conditions, then we cannot do better, right? Now, if there are some weird conditions and so on that are applying, that are reducing the size of one relation, maybe. But for a basic join, select star from n plus n, where some kind of ID is some kind of ID, we can't do better. We have to read everything at least once. But this basically is the case where one relation fits nicely in memory. And again, remember this drawing here. This is quite often the case. But even if you are joining this, it's very likely in today's databases that all of this could fit in memory at the same time. So you can have 3 hash tables in memory, customers, projects, employees, and you just probe one after the other and output the whole thing. All right, next thing. The size of the file is 2 times the buffer size. So the file is basically bigger than memory. How do you do the join with hashing, and what would be the IO cost of this? Draw. Now we can find out who's the fastest draw in the Wild West. M is much bigger. It can be very large. And so actually, let's go back to this. It's a very good question. I forgot about this. Does the value of n matter? The size of n didn't affect the cost, other than, of course, being in the formula? No. Because all you're doing is probing. So in this case, it's really the smaller relation that's impacting the cost. Okay. If you had and here and some constraints, yeah. Yeah. If you want to reduce the number of IOs with a constraint on n, then you would need some kind of index or something. And typically it wouldn't be worth it. So, yeah. All right. So let's go back to this. Draw the execution. It's a little bit more complex than before. We'll try to visualize the execution of the hash join as we talked about it on Tuesday. And then think about what's the IO cost. Think about whether. So the question is, when you're probing, do you always need all the buckets? Think about that, because I don't think you do. And the question is, why don't you? Because of the hashing, because of the way the hash function is constructed. Then I think you can get away with keeping one bucket in memory. So, but go and draw and see what you come up with. Right. Okay. So it's not clear. So there are 2 rounds of hashing, and so for one of them you don't have to do this. For the second one you do. So. Some average IO cost. Well, I can draw and then we'll come back to this. I think we're always using average IO cost when we're counting the IOs. It's always just average. The question is whether you need to be reading back and forth. Can you read things into memory once and they stay there? So, do you remember how we did the hash, the double hashing? We basically applied one hash function and we call this a partition phase. And then we take these partitions, we write them to disk. And then we would read one at a time. Yeah. Something like this, yes. So again, we have M and we have N, and then it's fairly large, right? And we know now that the B thing is small, right? And it's roughly half of the M. So one way to do this is to say we will create a hash table here, but it's too big to fit in memory. So what we'll do is to write the buckets to disk. So we have one bucket here, another bucket here, one here, and so on. With me? How many buckets do we have? Well, we have, we could have up to 2 B buckets, right? Roughly. So it's something smaller than that or equal to. Because that's, if we assign one block to each, then we can write them out. Basically, if we have one buffer to each bucket, then we can have this. Okay, so the next step is what? We basically need to do the same thing here. Apply the same hash function. And what do we get then? We get on disk buckets, except that these ones are pretty big, right? Because this file is quite a bit bigger. But it's the same buckets. And so if you have something with ID equals to 23, and that goes to here, then for ID equals to 23, that's going to go to the corresponding bucket, right? Because you have the same hash type function. And so I think that kind of answered your question. When we are doing the first hash, we need to keep the front in memory. But when we start to merge the things, then we can keep these 2 in memory at the same time. So that's the second phase. All right, so we have these big buckets. How many IOs did we need to do this step? Yeah. So far we have 2 times n plus n. So basically just to do the partitioning. And then we need to do the join, which is what you're getting at. And So we do the join by taking this thing again into the memory and doing a hash table. And we have a different hash function, remember. We need a different hash function. Otherwise, everything goes to a single bucket and we're in a bit of a trouble. You know, it would compute, but it just is slow. And once we've done this, we can take this bucket here and do the probe and output the join. So that's just take the first bucket here, read that into memory, and then we take the first bucket here and we probe. Well, I mean, if you look at, yeah, a little bit. I mean, what would be the size on disk here would be basically m times f, and this would be n times f. So you get this slight increase in the number of IOs. But roughly, it's roughly the same still. This is all on disk. Yeah. Also the red one. Yeah. Because, excuse me, also the blue one here. No, this is basically, that's your B. That's in memory. Yeah. So basically what we did in this part was to make like subrelations with hashing. And they have the property that each subrelation of M matches with exactly one subrelation of N. And the subrelation of M is small enough to fit into buffers. So this is the property. Because you're using the hash function, you're guaranteed that thing in the bucket 0 of M will only match with bucket 0 of N. That's really important to know. You don't have to look at, for bucket 0, you don't have to look at bucket 1, 2, 3, 4. You only have to look at bucket 0. Yes. When your bucket is small enough, or when we call this actually partitions in the intermediate, but it's basically a bucket, but it's just too large to fit into memory. And so when your partition becomes small enough that the hash table will fit in memory, then you start probing. That's correct. Yes, you may need to have many of those hash functions if your file is really humongous. If your smaller file is really big, then you might have to do the partitioning 3 times or 4 times and so on. So in that case, you need 3 or 4 different hash functions. So yeah, exactly. So the point is that the tables get smaller and smaller as you do more and more partitioning. If you have really bad data distributions, for example, if you think about a table where, if you're looking at the sales and everything has been sold by one employee, then no matter how many times you do the hashing, it will always go to the same bucket. And so in that case, you're in trouble. So in that case, actually sorting might be better, or just a nested loops join might be just as good. But basically, if you have decent distributions, then the partitions will always grow smaller, and eventually you have something that fits into memory. Now, so once you've done this, you've done all the joins from bucket 0 in both files. Then you can read in bucket 1 and you can create the hash table. And you can read in bucket 1, and you can probe and do the join. See what I'm getting at? And then you read bucket 2 from M, and you read bucket 2 from, and create the hash table, read bucket 2 from N, and you probe. And so you go linearly through these until you're done. And it's really important to remember that the only matches you can have are between buckets of the same number, because both are done with the same hash function. And that's really the key. You're guaranteed that things that have the same, and that they have the same value on the hash attributes, because you have equality, they will be in the same bucket, or the corresponding bucket. And so you basically read through here, creating new and new hash tables, and then interleaved, you read through here and do the probing and output the joint records. So how many IOs do you need for this? You need n plus n basically. I mean, technically you might need a fudge factor, but basically we go with the cost being 3n plus n. Because when you're writing the buckets, you can basically just write the pages that you need. And so you don't have to worry about the f factor too much. Mm-hmm. Okay, so to be able to do this, the smaller relation, sorry, go again. Yeah. Yeah, okay. 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 So I think basically you have a hash function here that is creating your partitions. And then for each partition, you apply a new hash function, h1. Sorry, there was someone here, there was a blue one. And you need to be very careful when you create this hash function that it's so different from the previous one that it distributes very nicely. That's to avoid the collisions. So if you have good hash functions, then I mean there's the fudge factor is because you have collisions in that some buckets are bigger than your average. So you're thinking about the number of slots in the tables. Basically, in both cases, the number of slots is very similar. Because here, the slots are just representing a buffer. Whereas here, okay, here you need to fill in. So, but basically the slots are roughly B divided by F. So just assume you have a roughly 1 page per bucket. In the first case, the 1 page per bucket is a buffer to write to the disk. In the second case, the 1 page per bucket is the bucket. Because in the second case, it actually fits into memory. Yeah. So when you have this much data, the bucket really, the hash function really has to be good. Yes. Now, I mean, the hash function basically gives you an offset. So you could just say, let's just make an array. And if you have overflow, then you might have just extra space at the end to worry about the overflow pages. So that would probably be the structure you have. Just like 1 bit to say if it's overflowed, and if it's overflowed, then you have a buffer pointer somewhere, something like this. Or you might allocate a pointer to which is null if you don't have an overflow. But then just do an array, because that's, you get direct access with the hash function. So yeah. So excellent question. So, but again, does the value of n matter? I mean, it sort of matters, right? Because it's in the formula. But did your memory requirements depend on n? No. Again, it's the size of the smaller table that's important. Because what you need to do with n is indeed you need to partition it. But what happened is that just the buckets were very large. And because in the second run, you don't need to store them in memory. You just need to go through them and probe. It's okay. It's okay if the buckets are very large. They could be huge. And you're just going through them, and you need one record to probe, and then you get the next record and so on. So you just need a small buffer to read through them. And that's really key. That's why the value of n is not important. It's a smaller table that dictates the performance of hasQ. With me? All right. So I had similar thing with 4b. You want to do this? You get the hang of it, right? It's just, you would have half as few buckets, right? No, half as many buckets, sorry. Here you just have half as many buckets, and each would be half as small. That's the only difference. So let's not go through this. Okay, let's go to this one. Assume that the file is basically b squared. Let's go to this one. Let's do something interesting. So b squared is less than m times twice the Fudge factor, or the Fudge factor squared. You see what I'm getting at? What would you expect if you look at this? Are the partitions going to fit in memory? So do the drawing. Try to figure out how would you implement a hash join when the file is basically bigger than the memory squared. What's going to be the size? How many partitions can you fit? How big are they going to be, etc. All right. Maybe we go with this one. Start with this one. So from the one we did before, we just doubled the size of memory. That's it. For this one, I think you can get away with the same number of rounds for this one, but see if you can, what comes out of your drawing. How big is each partition and how many are there? So how many partitions can you make in the first round? You need one buffer per each partition. So how many partitions do you have? You have B, right? Because you have B buffers. So how many pages would be in each partition? If you have B partitions and your file is give and take 4B, so you get roughly M divided by B, right? What is M? It's roughly 4B, right? And so you basically have 4. With me on this? So that's sort of a rough calculation. 4 pages per partition. Now, so this is for M, of course. For N, how many partitions do you have? Well, let's just first look at how many partitions. So then we worry about the size later. How many partitions? Yeah, because we have the same hash function. Yeah, and then you're getting to what's the size, how many pages, and then of course we just have n over b, and we don't have a nice formula for this because we don't know the size of n. But again, it doesn't really matter. And then, so that's the first round to create the first partitions. And then in the second round, of course, 4 pages, that means we need 5 buffers, right? Roughly. It's a very small hash table. Clear. But the same thing, IO cost is 3 times m plus n, because you needed to read the whole thing, do the partitions, write the partitions, then read the partitions and do the join. Okay, so let's look at this one. We have m times f square is equal to b square. How many partitions? What's the size of a partition? We have the m here, we have the n here, and we have a tiny little b. When we do the first hashing, how many partitions will we get? Yeah, we get b. It doesn't change because b is the number of buffers. Doesn't matter. How many pages? Per partition. Yeah, we got b. B squared over b, which is b. Yeah. So roughly, you get b squared. You get b pages per partition, which is nice, right? Because that means it can roughly fit into memory. I mean, it's basically the number of partitions is b divided by f or something, and then so. But this means that the second page, the partition, actually fits to memory. And so that means you can do the whole join in the next round. So what's the IO cost then of this? So this one is to read, it's 2 m plus n, right? And then when you do the final join, it's m plus n. So you're still with the 3 m plus n. With me? You do the partitioning, which is 1 round to read, 1 round to write, and then you do the joins of the partitions, which is just 1 round to read. Now, then we go to what if it doesn't, what if it's bigger than this, bigger than the last one? And again, so we have the m, we have the n, and we have an even tinier b, relatively. So how many partitions? B. CC. How many pages per partition? Now somebody's going to scream at me for writing badly, but I always write the same thing. Anyway, how many pages per partition? Now, because there's a greater than. So it's basically greater than B. Right. So that means we're screwed. That means when we do the latter second hash function, we go out of memory. We cannot fit a single partition into memory. What do we do then? You had the idea at some point, I think. Just partition again. So instead of we do H and then H1 and then H2, new hash function. What's the cost? One more round of reading and writing, right? Yeah, you basically end up with log behavior. I mean, for this particular case, it's 5 n plus n because there's just one more round of merging, but essentially you get a log behavior. What's the difference between this log behavior and the sort merge? Remember what's the key difference between the performance? Big table versus small table. This log is of the small table, the other one is of the big table. But exactly, you just get this logarithmic behavior. It's exactly the same. Log behavior, yeah, exactly. Log of B. Now, good one. But again, remember, we have these cases where we have huge relations and small relations. And so it turns out that it's very rare that you go to this. It's really only when you have bad skew that you end up doing a lot of things. So, but this is the behavior. It just grows logarithmically, but of the small table. And this is really the big. So it basically wouldn't be better to do sort merge if you got into this. Again, it would depend on the size relationship. Because if one is extremely large, then sort merge join is dependent on that, and that might be 1 or 2 extra rounds. Sort merge join might be 9, whereas hash join is 5. So that is the trend. If you have 2 equally large, then it's going to depend on other factors. What SQL Server, for example, does is that if it finds out that the partitioning is not working well. So if you have skew in your data, it's going to switch to sort merge join, but only for a particular partition. So just dynamically say, okay, this partition is just not shrinking. So let's just do a sort merge join of that. Because of the properties of the hash function, you can do this. Mm-hmm. Yeah, right. So you're saying if one of the tables has a clustered index and it's already sorted, then that would be a good reason to do a sort merge join. For example, if you're doing a join and the huge table is sorted already on your ID, you're in good shape. Because sorting this you can do in memory, you get n plus n. So, and even though hashing is cheap, there's still a hash function, whereas the other one is just a comparison. So in some cases, when you do have clustering, then yes, sort merge join would be a good idea. But that's, because you pre-computed part of the work. So now, if I tell you we want 2 rounds and I'm giving you a B, what's the largest M you can sort, that you can hash join in particular time? It's roughly, yeah, so there's an F somewhere in there. It's probably, square root of M is smaller than B over F or something like this. So you need to account for the fudge factor and so on. And so you can go back to the things we did and convince yourself of this, because we have a couple of minutes left and I want to get to one more thing. Yeah, that's the square root. Yes. So we had the square root behavior with the sort merge join also, remember? And then here we have a square root behavior also. If we go beyond square root, then we go sort of to the logarithmic behavior. And again, the value of n doesn't matter. It's just the smaller one. Now, what if, let's go back to this case. Remember how we had what? We had B partitions, right? And which meant that we had 4 pages per partition. Remember this case? And we did something kind of silly, right? We wrote everything to disk and then we read everything back in. We don't really need to do that, right? So we could, for example, just say, do a slightly fewer partitions and then keep some of them in memory. Let's say we have B over 2 partitions, and each of which is 8 pages. And then we just say, well, we're gonna keep a few of these in memory. So the memory will be like this. We'll have the heads of some partitions, and then we'll have some full partitions. See what I mean? Just allocate some buffers to keep things in memory. And in that case, we have some things on disk, some things in memory, and the probing we can do immediately here. So just use as much memory as we can to keep partitions in memory. And then those partitions we can't fit in memory, we write them to disk. Yeah, if M is somehow in the middle, if M is bigger than we can fit into a simple hash join, but it's much smaller than we need the full double hash join. And we can actually do this dynamically. We can just say, and this is actually called the Grace hash join. We just try to keep partitions in memory. If we find that we need more memory, then we just add more partitions to disk. But we keep as many partitions as possible in memory. In that case, when we do the probing, those in memory we probe immediately and we give the answer back. Those that have to go to disk, we put them on disk. So if we have a case where we have the initial partitions and these 2 are on disk and these 3 are in memory, when we do the probing, if our hash function goes here, we write the output. If our hash function goes here, we write to disk. And that means at the end of this, we will have done all the joins here, and these partitions will be on disk, and then we need to read them into memory and do the join. So this, if you see anywhere a Grace hash join, that's exactly this. It's basically doing something intermediate between the simple and the single and the double, or doing something intermediate between the double and the triple. So it's just trying to avoid putting everything to disk. That's it. All right, so we did spend the whole class, I think, on this, which is good because it's useful. And I want you to be able to have this in your fingers. I want you to be able to do these kind of calculations because occasionally they are important. And I've done them in industry. It really turns out to be important. So we observed sort merge join. We did the square root of larger. We tried to do the small optimization to avoid sorting completely. Remember? Hash join, square root of smaller. And then we had the Grace hash join again to avoid writing some partitions to disk. So it's kind of a similar thing. And I want you to be able to calculate the costs, joins, sorts, selections, all the stuff. There's a formula sheet that you will get with your midterm exam, with your final exam. It's on the web, so print it out, keep it by your side. I believe there's a bug in there. Might be a couple. So the first one to report a particular bug, get some extra credit. So 0.5%, for example, might be enough to get you over to the next grade, if you're lucky. So have fun, find the bugs, please. Debug for me.